leverage your USB devices for USB post-DUT verification. In transaction-based verification, virtual transactors are leveraged to model real-world prefers. Though the transactor provides both functional model interfaces, typically user-level test benches are required to be created to model the actual traffic over that protocol interface. This is not a trivial task. The complexity increases substantially for advanced protocols such as USB and PCIe. This complex software test benches control and program the transactor that interact with the DUT, the general test, and simulation or emulation domain. This paper explores a novel method how a real USB device enabling real-world stimulus can be interfaced with a USB device transactor verifying a USB host DUT so that the user-level test bench does not have to be written. At the same time, we can leverage the full benefit of the transactor-based verification. Introduction. A transactor is a transaction-based verification solution that is developed for verifying the DUT. So a verification engineer creates a user-level test bench that would instantiate a specific protocol transactor and would leverage the transactor APIs to drive a stimulus to the DUT and response to a request from DUT. USB, Universal Serial Bus, provide an interface to connect the multiple prefers devices. USB device will be the personal computer, USB host. A USB device is characterized by its class code, subclass code, and protocol code. During an enumeration, USB must lead the USB device characteristics. If the USB host supports USB device functionality, it loads the host-side device driver needed for communicating with the device. As of today, USB supports 21 device classes. Each device class supports multiple device subclasses, and each subclass supports multiple protocols. A verification engineer verifying a host-side device driver needs to develop a new device test bench that fully implements prefers devices functionality, which is a complex task. We look at how we can have a virtual solution that enables USB device transactors to interface with a real USB device drive to avoid the complex task of creating multiple device test benches while ensuring all different use cases can be validated. The solution leverages Linux USB host subsystem to create a virtual adapter that can connect USB device transactor software with a real USB device. Currently, the solution is developed for a USB mass storage device that supports bulk-only transfer (BBB) protocol. The solution can work in both emulation and simulation domain. This approach can potentially be extended to leverage other protocol transactors to connect to our respective real-world interfaces. Chapter 2 is a USB device transactor. The USB device a transactor would typically consist of a hardware and software component. The hardware is written in synthesizable system Verilog SV, while software is written in a C and C++ language. The hardware part of the transactor connected to its corresponding software part through the SV directory programming interface, SV DPI. This communication across the hardware and software boundaries is at a transaction level leverage SV DPI. This also ensures that the USB device transactors can run in both simulation and emulation. The USB device transactor software in our work framework consists of two parts, C library and device testbench, and USB device transactor C library has DPI functions and user-level APIs. The device testbench calls user-level APIs to compute the USB device transactor and register user-level C callback functions for different USB requests. Since most of the USB requests require user input, hardware part of USB device transactor passes the USB request to transactor C library via SV DPI functions. The C library involves the register do or register the user callback C functions in the device test bench. Device test bench understands the USB request to prepare the response and queues them back to the USB host DUT via USB Device Transactor. So a USB request can be a standard description request or any device class specific request. So the figure 1 is the device transactor test bench. USB support in Linux. It is important to understand the USB support in Linux OS, the available and relevant open source libraries that helps interface with the device drivers to define how virtual device transactor can be created. The Linux operation systems OS provide support for both the USB host and a USB device. The Linux USB host subsystem consists of 3 layers of drivers. Host controller device HDC and USB core and device driver, the HBC and the USB core operate in kernel space, while the device driver can operate either in kernel space or in user space. A device driver, which is the top layer in USB stack and controls the attached USB device, is a host OS. The Linux also provides a virtual file system switch VFS software that provides the file system interfaces to user space programs, allowing them to access kernel internals. USB core creates USB usbfs through which it exports the kernel data structure and attaches the USB device for information to user applications. A device user operating in a user space generally uses files in a USB VFS, usbfs to interact with the attached USB devices. Figure 2 shows the Linux USB file system connecting user space application in user space and USB framework in kernel space. Figure 2 is the Linux file system connecting the user application with the Linux USB framework. The Libusb is an open source host-side C library that provides application programming interfaces APIs for the device driver development in user space. The APIs across the platform and the user mode. The USB library is well-paralleled and encapsulated OS level details and the USB protocol complexity from the device driver developers. In the Linux platforms, the USB library access kernel data structure and attach the USB device information through the Linux USB file system via usbfs. Figure 3 shows the library USB interaction with the user application and Linux USB file system. As Figure 3 is host-side C library interconnect user application with the USB file system. 4 is the USB device virtual solutions. To enable the functionality of the leverage of the transactor to interface with the real-world devices, we highlighted the approach. We've taken the overall architecture. We've leveraged the Linux USB framework and the library USB to create a USB device virtual solution. The solution acts as a bridge between the real USB mass storage device and USB device transactor. The USB device transactor C library supports USB request from a USB device transactor hardware in virtual adapter. The virtual adapter is a user space device driver that processes the information communicated with the real USB device through the live USB and provides a USB response back to USB device transactor hardware. Figure 4 is the device virtual solution connecting USB mass storage devices and device transactor. And for the out transfer, the data bytes are stored in the attached real USB device. While in transfer, the data bytes are fetched from attached real USB device. Figure 4 showcases device driver virtual adapter that links the USB device transactor C library and real mass storage devices connected to host PC. Virtual adapter. This section describes how virtual adapter interfaces with the USB device control transactor C library on one side and the right side and the other side. Users can adopt the similar procedure to develop the VA to interfaces with the user's PFM on the one side and live USB on the other side. Users VA interface to the live USB should be analog to the VA interface described here, but each interface uses BFM and can different. Since such a USB device transactors needs to support both emulation and simulation, we have employed SV DPI interfaces to communicate across the transactor software and hardware components. For pure simulation and the other mechanisms such as SV interface can be also used to connect to software and hardware parts. The VS consists of the 4 parts: initialization, enumeration, and data transfer, and instruction. One is initialization. To create a configured USB device transactor object over user device's software. Initialization, live USB live using the live USB underscore init. This API creates a data structure and must be called before calling any other function. Figure 5 is the live USB initialization. C. Live USB library with the real USB devices using live USB underscore open underscore device underscore with the VID underscore PID. User can get a vendor ID and a product ID using a LSB command on Linux terminal. The LSUSB lists the USB device USB devices attached to USB host. On successful connection with the real USB device, we get a real USB device context corresponding to USB devices. The context is used to follow or the future interaction with the real USB device. There are other APIs as well, which user can use to connect to live USB with the attached to real USB device. Figure 6 is a live USB opening a USB device. To USB device enumeration. Once the linkage is established between the USB host DUT and the USB device transactor, USB host DUT device driver will enumerate the USB device through the USB controller transfer. VA will get these USB controller transfer from the USB host DUT via device transactor software and invoke the corresponding live USB underscore star underscore descriptor APIs to retrieve all descriptor from the real USB devices. VA provided a vast set of the APIs to get a various device descriptor from the attached USB device. Figure 15 shows the few examples how VA gets a descriptor from the real device using live USB APIs. Figure 7 is the live USB API getting the USB device and both descriptor from the attached USB device. Once the USB and the host DUT device driver has received all descriptor, it will issue the SET configuration command marking and of the successful enumeration. VA issued the library USB underscore set underscore configuration and library USB create the interface, or the set configuration and interface with the real USB device. Figure 8 shows the VA setting configuration interface in real device using library USB APIs. The Figure 8 library USB API setting configuration in real USB interface. USB transfer library USB provide 2 interfaces, and synchronous and asynchronous, for USB data transfer. Synchronous interface is blocking, while the asynchronous interface is non-blocking. When a host DUT sends a USB transfer, device transactor hardware relays USB transfer information to VA using the device transfer software. VA uses live USB synchronous interface to perform a USB transfer operation with a real attached USB device. The USB transfer through the asynchronous transfer consists of 5 stages, creating a callback function that gets called when a USB transfer is complete. Create a live USB transfer struct. Fill library USB transfer struct. This step also registers the callback that needs to be called when the USB transfer is complete. Submit the filled library USB transfer struct to a live USB. Once the USB transfer is complete, live USB invokes the callback indicating the status of a USB transfer. Figure 9 shows how VA issues the bulk out transfer is performed. VA created a complete callback function CMPLT out CB. As once VA gets the data byte from a USB live USB submit transfer to fill the data information and submit the transfer. Once the USB transfer was complete, live USB would call the completion callback CMPLT out CB, indicating USB transfer status. If the library status was able to successfully store data bytes in the attached USB real device, the state would be a 0. If the USB transfer did not complete within the timeout, VA cancels the transfer and issues the USB store command back to USB host DUT, and similarly USB Birkin transfer are also performed. This is the figure 9 is live USB API's setting configuration of a real USB device. The structure. When the test bench has called the VSD structure, the code live USB can close. This will destroy all the handles corresponding to live USB. Figure 10 is live USB closing USB real devices. As a USB host, chapter 6, a USB host DUT verification with a USB device virtual solution. Now that we have the USB virtual device transactor solutions, we will describe how we will leverage it to verify the USB host DUT and how such a verification environment needs to be created. The host DUT verification environment would consist of the host DUT and device transactor, your USB device, and a device virtual solution as primary components amongst the others. For demonstration, host DUT software and hardware have been replaced with the host transactor. In the emulation domain, host DUT and device transactor hardware parts are integrated, compiled, and synthesized on emulator, while their corresponding software parts execute on host PC. The real USB device is attached to host PC. Figure 11 shows the interconnection among the different components in host DUT verification environment in emulation domain. Figure 1 in host DUT verification environment with the device virtual solution in emulation domain. In the simulation domain, the hardware and software parts of both the host and DUT device transactor execute on host PC. The real USB device is attached to host PC. Figure 12 shows the interconnection among the different components in host DUT verification environment in simulation domain. Figure 12 is the host DUT verification environment with the device virtual solutions in the simulation domain. A. Verification environment setup. Following the code flow of a USB host DUT verification environment. Test bench environment, the setting. So the connect a real USB mass storage device in a host PC. Obtain the USB real device vendor IO ID and product ID. Linux command ls USB can be used to get attached to devices vendor ID and product ID. Host DUT device transactor test bench. Edge integrated USB host DUT and device transactors hardware in the user environment. Compile the host DUT and device transactor. So create a host DUT software and that will enable the host DUT. Wait for a link up between the host DUT and device transactor. Initiate the USB data transfer from the host DUT. Create the device transactor test benches. The API mentioned in this section are specific device virtual solution. These APIs encapsulated the live USB APIs. These APIs would be different from a user for developing their own virtual solution. They are showcased here to highlight that the device test bench logic would be minimal when the library USB and real USB devices are leveraged to verify the host DUT. B. Create and configuration USB device virtual solutions object. At this point, VA will initialize the library USB. Let's connect the USB device virtual solution. At this point, the USB host DUT transactor will be able to detect USB devices and establish connections with it. During the execution of this API, VA will open real USB devices and will be able to send the response for all control transfers. D. Learn USB device virtual solution is continuous loop. Whenever the USB device virtual solution hardware wants to interact with its software, it raises an interrupt. The interrupt is generally raised when the hardware receives a USB request such as executor or USB transfer from the USB host DUT. With every loop call, the USB device virtual solution software checks whether hardware raised an interrupt. If an interrupt is raised, device virtual solution software processes the interrupt, calls live USB APIs to interact with attached real USB device, so that the loop should be called continuously in a loop for full duration of the test. The figure 13 is test bench code running device virtual solution. Device virtual solution will keep responding to host DUT USB request. B. Verification environment result. The high-speed HS USB mass storage device was inserted in host PC. The real USB device supported for SCSI transparent command to set using the BBB protocol. Device virtual solution established connection with the USB mass storage device using the device's vendor ID and product ID. After USB connection between the USB host transactor and the USB device transactor, the USB host transactor test bench initialized and enumerated USB mass storage devices. Post-enumeration, a USB host transactor ran few SCSI command and transferred and received 1800 kilobytes from the USB mass storage devices. Responses from all USB requests, USB control and bulk transfers came directly from a USB mass storage device. Apart from initialization and running a service loop, verification engineer did not have to write any code logic in device test bench for generating responses. The test at a high speed, HS speed, completed in 5,702 seconds in simulation, whereas it took 23 seconds in emulation, making it approximately 248 times faster in emulation. Similarly, USB host transactor was verified for the super speed access by replacing the HS devices with SS devices. In SS speed, 3600 kilobytes were transferred. The test at SS speed completed in 4,815 seconds in simulation, whereas it took 16 seconds in emulation, making approximately 301 times faster in emulation. Chapter 6 is the future work. The current device virtual solution has been developed for mass storage device following the BBB protocol. Since the library USB drive provides a generic framework for usual USB driver development, the solution can be enhanced to verify the host DUT USB for other 21 device classes, each device class supporting multi-device subclasses and each subclass supporting multi-protocols. A similar approach can be taken up to enable interfacing with other real-world devices for the respective protocol interfaces, such as timers and etc. Timers and etc. can be configured if necessary to address slow simulation performance and timeouts when a solution is deployed in simulation for specific devices. Chapter 8 is conclusion. This paper shows how USB host device driver and USB host DUT can be verified with a real USB device using device virtual solution in both simulation and emulation environment. So specific result using a real USB device were enumerated. Once basic host DUT functionality is verified using the traditional mechanisms, such a solution can easily cover multiple systems level use cases easily and effectively helps DUT respond to real-world stimulus. In this case, verification teams using a virtual solution does not need to write complex test bench and test cases. The paper presents a crisp set of the steps on how users can develop their own virtual device solution using available open source library like Libusb. Okay, thank you. Today I read this paper as leverage real USB devices for USB host DUT verification from the Synopsys in DVCON2025. Yeah, thank you for your time. See you next time.